All right, so I wanted to go over continuous charge distributions and how we can find the electric field when we have that kind of situation. There's going to be a couple separate videos that you'll be available to you. But first of all, I just wanted to address the fact that we had a lot of questions about what do we mean by a continuous charge distribution. And in fact, even the description in the text caught people by surprise or confused them because, they said that previous, until they got to the section on a continuous charge distribution, they said that the charge distributions were discrete and they were made up of individual point particles. And so I think that if we sort of keep that in mind as a contrast, that there are different ways for the charge to be located. It can be really literally at a single point, which doesn't really have any dimensions, which I know doesn't make sense, but that's sort of the model that we're using, that is just located at a single point, versus situations where our charge is going to be spread out over an area or a line or a volume. And those are the types of situations that we're talking about where we say that the charge distribution is continuous. So just to sort of contrast the two, when we started the chapter, we were really concentrating on the ideas that we see on the left-hand side, where we think of just a single charge, it's located at a single point, and we're thinking about the electric field that it produces. We don't even really have to do a lot of thought. We found that the electric field due to that point charge was equal to 1 over 4 pi epsilon naught times that charge over r squared. That was the expression that we used for the electric field. This takes into account that the electric field becomes inherently stronger if we have more charge on our point charge, and it also grows weaker as we grow further away from that point charge. And these electric field lines shown on this picture do mimic that, because if we go further away from the charge, you see that there are less lines per unit area. The density of lines goes down, indicating the electric field gets weaker. Now, on the right-hand side, this is where we have a charge distribution, because here we don't have a point charge, we just have a big old blob of charge. And so we could say that the total charge represented here in this entire volume is just Q, but it's not located at a particular point. In fact, it's all spread out. And in this case, we're thinking about something three-dimensional. So if I wanted to find the electric field due to this smeared out charge, if you will, the best way to do it is to take little pieces of charge, like here, and we'll call each of those little pieces delta Q. And then we want to know the electric field at a particular point. Here we want to know it at point P. And so we draw a line from the charge to that point. That's the line along which the electric field will be directed. And so delta E, so the electric field due to that piece of charge is 1 over 4 pi epsilon naught. And then we write delta Q over r squared. And we're also going to use the unit vector r to just represent that this is the direction. It's along the line between the little piece of charge and the point where we're trying to find the total electric field. Now, in order to find E total, we would have to do some sort of summation of all the delta E's, which are vectors. So it would be a summation of 1 over 4 pi epsilon naught delta Q over r squared and r hat. And so as we do that, we have to look at little different pieces. So like right here is another delta Q. But if we look at the line along which that would act, that would create an electric field that would be a little bit differently pointed. And we would have to go through the entire object so that we took it and divided it up into as many little pieces as we could make. And then we would have to add up all the contributions to the electric field, and we would have to add them like vectors, which means we have to pay attention to the direction. And if we think about where we're going with this, usually mathematically, when we start breaking things up into small pieces and then adding them together, we realize that, for instance, this curvy blob of charge really wouldn't be well represented by little pieces that were cubes, because as we got to the edge, we would see that the cubes didn't really represent the shape very well. And so we really want to let those delta Q's get really, really small. And so instead of looking at the delta E, we're looking at DE. And therefore, finding E total, instead of doing a summation, would be found by doing the integration of dE, which would be 1 over 4 pi epsilon naught times dq over r squared. And so that really becomes the essence of what our problem is when we're trying to, when we're looking at a continuous distribution, is that we are looking at a case where we have to add up all the little contributions in a mathematical way through integration. But the other thing that we have to worry about is, as we're adding up all these electric fields, we have to worry about what direction each little piece contributes and what's going to be the total sum and the total direction of the electric field. And last, well, what becomes a primary concern is, how is the charge being distributed? And that's what we look at here, is the charge can be distributed over different sort of geometric type ways. So in this case, our charge is distributed over a line. And so typically, so this might be a line of charge, we use the term lambda, which is representing the charge per unit length, which means if I have a little piece of it, I'm going to find a little piece of charge dq from a length of dl. So here's a dq, and it's from a piece that has a length of dl. So that's one way that the charge can be distributed. Another way is we can spread it out over an area. And so here's the area. And typically we use the Greek letter sigma to represent the charge per unit area, or dq over dA. And then finally, we can have our charge distributed over a volume, which typically we use the Greek letter rho to represent the charge per unit volume, which is equal to dq over dV. So all that we're doing here so far is I'm showing you these are the different ways that our charge can be distributed. Notice that it represents dimensionality. So if I distribute my charge over a line, it's really only distributed in one dimension, like over a single variable. And again, we use the Greek letter lambda to represent how much charge there is per unit length. And in a minute, I'll show you that that's how we rearrange these expressions to find dq. We can have the area, where sigma represents the charge per unit area. and finally the volume, where rho represents the charge per unit volume. Now in this final picture, they're pointing out, for instance, if I had a sheet of charge, when I'm looking at these little pieces of area, which also would represent a bit of charge equal to sigma dA, notice that because of the symmetry of these pieces, dA1 and dA2, relative to point P, we have electric field 1 points in this direction, electric field 2 points in this direction. But you can see their x components are going to cancel out, and we get a total electric field in the vertical direction. So that also becomes some of the work that we have to do when we have a charge distribution, is figuring out ahead of time, in a particular situation, when we add up all the contributions to the electric field, can we say that the electric field will be strictly in one direction? For instance, in this sheet of charge, it's just going to be vertical in a direction perpendicular to the actual sheet. And that's something that helps us actually move forward with our calculations. So here is, again, sort of these charge distributions that were given in your book. I wanted to just call your attention to the fact that this was in the book. Again, remembering that lambda represents dq over dl. So that means that we can write dq as lambda times dl. And so really, in a sense, when we have a line of charge, we're going to split it up into little pieces that have a length of dl. And then lambda is going to be like a number. It might be something like, we might just say lambda is a constant, and so we can just leave it as lambda. Or we might see, oh, the linear charge density is 5 coulombs per meter, and we could put in the number 5 for lambda. Similarly, we have sigma is dq over dA, so we can rewrite dq as sigma dA, and again we have to figure out how to write dA. And finally, rho is dq over dV, and this means that dq for a three-dimensional distribution of charge can be written as rho dV. And so you actually see these being used down here. So they're sort of contrasting, when I have a bunch of point charges and I want to find the total electric field at this particular point P, I just add up all the contributions using the idea that each contributes an electric field of 1 over 4 pi epsilon naught q sub I over r squared. But if we have a line of charge, now we're going to do an integration, and instead of dq, I'm going to write lambda times dl. For a surface charge, instead of dq, I wrote sigma times dA. And then finally for a volume charge, we'll write rho times dV. So that's just how we get started. What you find is there actually are only a couple different types of problems that we can effectively solve using this approach, but we just want to get a sense of how the problems will be done. And I'm going to post a video or two of, how we would do some of these simple distributions, like a segment of a line charge, and then also talk about how we would extend it to an infinite line charge, and so on. In the next chapter, we're actually going to see a much easier way to do these calculations. And so you don't actually have to know how to do a lot of these, but I want you to get familiar with them. And so to finish up, I just wanted to look at an example and how we might sort of start reasoning through this. So they're saying this positive charge is uniformly distributed in a semicircle, and then we want to find what the electric field at point P is. So what we could do is we could sort of imagine, like, I'm going to take a little piece right here, and this represents dq, and then I imagine the line between dq and point P, and then the electric field due to this piece I can write as dE. And the idea is that I would sort of do this all along the path of the semicircle. But I want to point something out to you. Because of the symmetry, I could find a dq on the other side of the y-axis that is pretty much a mirror image of the one I found on the left-hand side. And so that would produce an electric field dE. That if you look at it, those two pieces are like symmetrical about the y-axis, and you could divide this whole semicircle into pairs like that. And in the end, we would find that the total electric field due to that whole semicircle is going to end up just being in the y direction, the negative y direction, because of the fact that all the x components are going to cancel out by their symmetric pair. And so that's how we would find that total electric field. So look and for some of the videos of how we actually do some of these integrations. It's good practice to start to try to follow along the steps that are used to do the calculations. In the end, often when you do a problem, the book has already worked out how you get to the expressions for the electric field, and then you just have to fill in the variables or the constants for your particular problem. So for a line segment with a particular length and a distance away from it, all those are terms that are in the expression, and you just have to put in the proper values for your particular problem. Hopefully this makes the idea of the continuous charge distribution a little more clear and makes you feel more comfortable with it.